everyone, so my journal club presentation is on the topic of prodrugs, and specifically in this article they used a multi-drug nanomedicine made of the prodrug squalenoid gemcitabine, and then they used this to encapsulate endelphysine. And so before going into this article, I just wanted to provide a little bit of a background. And so as Dr. Miller talked about in chapter 14, prodrugs are used to protect the pharmacophore in drugs until they get to their site of action. And so prodrugs are an added group to the drug that can decrease the side effects as well as protect the drug from metabolic enzymes. And so also prodrugs are often used when the drug contains functional groups such as a carboxylic acid or other functional groups that cause them to not be able to diffuse through membranes easily, but they are still essential to the pharmacophore. So prodrugs can then be used to mask this functional group, allow them to diffuse through the membrane, and then they can be cleaved once they are absorbed in the bloodstream and back into their active drug. And so the researchers in this study actually assembled a self-assembling prodrug, which is shown in the B portion of this figure here. And so once the prodrug is assembled, it will actually self-assemble into a nanoparticle. And so in this study, the researchers used gemcitabine as their drug, and so I'll just refer to it as gem for the remainder of this presentation for simplicity. And so gem is a nucleoside analog that is shown to be very active against a variety of tumors, including non-small cell lung cancer, pancreatic cancer, as well as leukemia. And so gem is a very common treatment against cancer, and it's actually the third most prescribed treatment worldwide. And so once gem is taken up by a cancer cell, it is transformed into its active form. And so this first figure here is gem triphosphate. And so once it is phosphorylated into its active form, it can then be inserted into DNA and inhibit DNA synthesis. This second form here is gemcitabine diphosphate, which can then be used to inhibit RNA synthesis. And so once it inhibits the synthesis, it then leads to programmed cell death of the cancer cell. However, before gem is converted to its active form, a portion of it is inactivated by metabolism in the liver and in the blood through deamination. Additionally, about 10% of the drug prescribed is also subject to renal filtration. Additionally, this drug has also been indicated to be susceptible to resistance, and this is because since gem is such a hydrophilic molecule, it is not able to diffuse through the membrane on its own. Therefore, it has to use this HENT1 transporter and able to permit entry into the cell. And when resistance occurs, this is when the cancer cells either alter or remove this transporter to prevent the cancer drug from entering the cell. And so the rest of this picture here briefly describes an overview of its mechanism of action. So gem is also referred to based on its structures DFDC. And so this figure shows it being permitted into the cell through those transporters. And then it is phosphorylated into its triphosphate and diphosphate active forms. And so these circumstances allow it to be an optimal candidate for bioconjugation into a prodrug. And so the researchers in this study used a derivative of squalene known as squalenic acid, and they bioconjugated it to gem. And so squalene is a natural lipid precursor in the biosynthesis of cholesterol, and it is therefore very biocompatible. So once these two compounds are bioconjugated, they will then spontaneously form a nanoparticle. Previous studies have indicated that these nanoparticles do increase the anti-tumor activity against leukemia and pancreatic cancer. And so these nanoparticles contain high activity in cancer strains that were considered to be resistant to free gem, because since this prodrug now is more hydrophobic, it is able to passively diffuse through the membranes of the cancer cells and no longer need these transporters. And so the researchers in this specific study, they took this idea one step further. And so previous studies have already been published about this SQ-GEM nanoparticle. However, the researchers consider that often in chemotherapy, a single drug is not used in the treatment. This is often ineffective. usually a multi-drug approach is considered. And so the researchers then encapsulated these nanoparticles with an amphiphilic drug that is distinctly different in therapeutic target from DRIM. And so the drug they chose was endelphocine, which is an amphiphilic alkyl-lysophospholipid, as demonstrated by this structure here. And so a complete understanding of the mechanism of cell death of endelphocine is not completely understood, but previous literature has indicated that it uses lipid rafts as scaffolds for the clustering of that Fas receptor. This clustering leads to apoptosis of the cancer cell. Additionally, although endelphocine has very high activity against tumors, it also comes with its own pharmacokinetic issues. So when administered intravenously, it does cause red blood cells to burst and lyse open. When administered orally, it does cause gastrointestinal irritation. And so these undesirable pharmacokinetic properties do cause it to be a good candidate for encapsulation, where these pharmacokinetic issues can hopefully be diminished and the strong pharmacodynamic properties can be the only thing that's observed when this drug is administered. And so utilizing nanomedicine to deliver these drugs to tumor sites do contain several advantages when related to free anti-tumor drug administration. And so nanoparticles are able to passively target tumor sites through what is known as the permeability and retention effect. So this idea is that when cancer cells are rapidly dividing, they're also driving angiogenesis through production of an abnormal amount of vascular growth factors. And this information comes from the citation lemmas at the bottom of the slide. And so once these blood vessels form, they are very immature and very leaky. As you can see in the figure on the right, you have those blood vessels lined with those cells are much farther apart. So it makes the blood vessel very leaky. And this is actually a good thing for these nanoparticles because they can then leak into the tumor site and accumulate there. And they're not going to be diluted by the lymphatic system because tumors also do not have a functional lymphatic system, which will allow them to accumulate even further in those tissues. And so this helps them, the drugs being encapsulated in nanoparticles will help reduce the pharmacokinetic problems and help them have a better biodistribution as well as decreasing off-target effects and undesirable side effects. And so just to sum up what we have done so far, the researchers have taken gemcitabine, an anti-cancer drug. They have bioconjugated to squalenic acid to form their amphiphilic prodrug, which will then be used to encapsulate endelphocine because this prodrug does spontaneously participate into nanoparticles. And so the researchers in this study, their main purpose was to determine if incorporating endelphocine in these SQ-GEM nanoparticles could produce a functional nanomedicine against tumors. And so in order to do these, the researchers first synthesized these nanoparticles. And so in order to do this, it is a very easy process. And so the SQ-GEM molecules are mixed in water and ethanol, and then the endelphocine is added dropwise to the stirred solution. Ethanol is evaporated out of the solution using a rotovap, and this does provide the aqueous solution of the endelphocine encapsulated nanoparticles. So the researchers first wanted to determine what ratio between the SQ-GEM and the endelphocine would be optimal, and so they did this through analyzing the size and the PDI of the nanoparticles that they formed. And so PDI is the polydispersity index, and it indicates the size distribution and the non-uniformity of the nanoparticles. So you want a low PDI for your nanoparticles below 0.3. And so in order to determine the size and the PDI of these nanoparticles, they used a technique known as dynamic light scattering. And so in this technique, basically a laser is used to illuminate these nanoparticles suspended in the aqueous solution. And because the particles are constantly moving, they are scattering light at a fluctuating intensity. And this intensity is measured and can be back calculated to provide the size as well as the PDI of the nanoparticles. And so from using dynamic light scattering, the researchers were able to obtain these results. And so as you can see on the x-axis, we have the ratios of SQ-GEM to the EF molar ratio. And then we have size and PDI on the y-axis. And so as you can see, when SQGEM is not encapsulated with endelphysine, it is just by itself. We can see it's at the largest size and the largest PDI. So these aren't optimal properties of a nanoparticle. When endelphysine is encapsulated, you can see that the size significantly decreases. And so this is because of the interactions that are occurring between the SQGEM as well as the endelphysine. And so if we look further into the size distribution of these nanoparticles in this figure here, we can see we have size on the x-axis and intensity on the y-axis. And this sharp peak here is correlated to the SQGEM endelphysines at a ratio of 1:1. So this high peak here indicates that a majority of the molecules are at that size and that there is more uniformity between those molecules. So as you can see, when we go from a 1:1 ratio to a 1:2 ratio, which is that black line, you can see that the size distribution significantly worsens. So the researchers took this information and were able to obtain that the optimal ratio is a 1:1 of SQGEM and endelphysine. Next, the researchers provided their audience with this table to summarize their findings so far. And so they also measured the zeta potential of the nanoparticles as well as the encapsulation percentage of the drug. And so like we talked about a little bit in Jay's presentation, the zeta potential is the charge on the outside of the molecule. And so as you can see, when these nanoparticles are measured for zeta potential, when it is just the SQGEM nanoparticles, they have a negative 17.73 zeta potential. And then when endelphysine is encapsulated, they have about a negative 12 value. And so the zeta potential is used because it indicates the stability of the nanoparticle over a period of time. And so the researchers in the study will further study this, but this indicates that their nanoparticles will be stable because you don't want a neutral nanoparticle or they will start to clump together. The nanoparticles being either negative or positive charge indicates they'll repel each other and be more stable, which is shown here. The researchers also measured the encapsulation of endelphysine as well as the gem, and as you can see, there were very high drug encapsulation percentages, which shows that endelphysine was encapsulated in the nanoparticle. And so the researchers also used TEM in order to verify the information shown in dynamic light scattering for the size of the nanoparticles. So as you can see here, when we have SQGEM nanoparticles, they are about 200 nanometers. And then when we add endelphysine, we see that the size significantly decreases, which verifies the data in the dynamic light scattering. And then the researchers also studied the size of just the squalenic acid nanoassemblies as well as the squalenic acid and endelphysine nanoassemblies. And we see that these B, C, and D are all around the same size. And we definitely see that once endelphysine is encapsulated in the nanoparticle, the size significantly decreases. And so in previous studies, it has been demonstrated the organization of the SQGEM nanoparticles, but the researchers wanted to confirm the particle formation. So they used negatively stained TEM analysis to further indicate the supramolecular organization. And as you can see here, the nanoparticles, they have this hexagonal organization. So that can be better interpreted through these pictures here. And so when you think about the hexagonal organization of these nanoparticles, in relation to the release of the drug, this is not going to be realistic for a slow release. And so we can also see that this mean lattice spacing is about 3.2 here. And so these are nanoparticles that are not encapsulated with endelphysine. We can see that they have this supramolecular organization, and when compared to nanoparticles that are encapsulated with endelphysine, we can see here that when they use the same TEM, it's really hard to tell what the organization is. You can't really see. And so then they used a type of TEM that has a much higher resolution, and they were able to provide the images shown in D&E. And as you can see, there's not really the same organization here. It's more of like a spiral or onion organization. And so this is really important because this is more of the organization that is shown here. And with a mean lattice spacing of slightly increased to 3.6, this indicates that the structure is a little bit more relaxed. And so the researchers demonstrated here that with this onion-like structure, the slow release of the drug is a lot more realistic, because when you think about like peeling an onion layer by layer, this is how the drug is also going to be released from the nanoparticle. So next, the researchers wanted to indicate the distribution of the drugs within the nanoparticle. And so they did this through X-ray photoelectron spectroscopy. And so in this technique, it actually indicates the surface chemistry of the nanoparticles per element. So as you can see in A, we have binding energy on the x-axis and core level regions on the y. And so this first one with F1S, so they measured the element fluorine at the surface. And so if we look back at the structures that are within the nanoparticle, we can see here that phosphorus is in endelphocene and fluorine is in the gemcitabine structure. So when we look at fluorine, when we see a spike, we can see here that that indicates that gem is at the surface of the nanoparticle. So with that red line, we are looking at endelphocene encapsulated nanoparticles, and so this indicates that gem is interacting at the surface of the nanoparticles. And we see the same thing with that black spike, which demonstrates the SQ gem nanoparticles, and so this makes sense as well. And then when we just measure endelphocene, we get that like straight up blue line, which indicates that there is no fluorine in that assembly, which makes sense because endelphocene does not have fluorine in its structure. When we move on to the phosphorus element, we see the SQ gem endelphocene nanoparticles do exhibit that spike, which indicates that endelphocene is interacting at the surface of the nanoparticle. When we measure just the SQ gem nanoparticles, we do not get that spike at all, and this makes sense because the SQ gem nanoassemblies, they do not have any phosphorus in their structure. And then of course, when we look at the structure of endelphocene, we will see that spike as well. And so this indicates that the surface chemistry of the nanoparticle is exactly what they're thinking. However, they also wanted to verify through another technique that endelphocene was effectively encapsulated. And so to do this, they used XPS in order to look at the inside of the nanoparticle through what is known as etching. And so over a period of time, they looked deeper and deeper into the nanoparticle. And so on the x-axis, we have etching time. And then on the y-axis, we have that phosphorus to fluorine ratio. And so looking back at the structures here, we can see that over a period of about 35 minutes, we get a ratio of 2 of the ratio of phosphorus to fluorine. And so this indicates that there's actually 4 times the amount of endelphocene in the center of the nanoparticle than there is of the SQ gem. And that is because for every 1 element of phosphorus, there are 2 fluorines based on the structures here. So we have to actually double the ratio presented. And so next, the researchers wanted to indicate the stability of these nanoparticles over time. And so the nano assemblies were analyzed for changes in PDI and size over a period of 60 days to indicate stability. And so remember that PDI is a measure of the size distribution or the non-uniformity of a sample. And so we want a PDI of lower than 0.3. And so first, the researchers measured over a period of 60 days the size change of these nanoparticles. And so as you can see here, this green line is the SQ gem endelphocene nanoparticles, and over a period of 60 days, their size does not change at all. And then the SQ gem, which is this red line here, you can see that in just about 10 days, their size goes from about 100 nanometers to 300. And so their stability is only going to be about 10 days because they increase in size significantly very soon. Then when we compare this to the PDI, and so this 0.3, we want it to be below that in order for the nanoparticles to be an optimal uniformity. And so what we can see by this picture here is that the nanoparticles encapsulated with endelphocene, they do increase in size distribution over 60 days. However, they never pass that threshold of 0.3, which indicates that they are still stable for the full 60 days. However, when we look at the nanoparticles that are not encapsulated with endelphocene, that red line, they quickly surpass that threshold in just about 10 days. So this indicates that these nanoparticles are not stable past about 10 days. And so what we can draw from this is that once we encapsulate these nanoparticles with endelphysine, their stability increases significantly. So now they are stable for at least 6 times more than they were initially, just from this test. And so lastly, the researchers wanted to indicate the activity of these nanoparticles against tumor cells in vitro situations. And so they used bone cancer cells in order to do this. And so in figure A, you can see here that first they just measured the IC values of the free drugs throughout the study. So free endelphysine, free gem, and then the combination of free gem and free endelphysine. And so as you can see here, we have concentration on the x-axis and cell viability on the y-axis. And if we first look at the free endelphysine, which is that light blue line there, you can see that we have an IC value of about 69. And then once we get to free gem, we have a much lower IC value. However, free gem gets to 50% viability, and then it just kind of plateaus. So I'm not really sure why this happens. The article doesn't really provide an explanation. The only thing I can think of is maybe this has something to do with the transporters that are used to permit free gem entry into the cancer cell, but other than that, I'm not sure how possible or accurate this is. And so moving on, when free gem and free endelphysine are used together against these cancer cells, we do get a much lower IC value, and it does surpass that 50% viability threshold. And so then the researchers looked at how the nanoparticles actually responded to these cancer cells as well. And so if we first look at that pink line there, which is the squalenic acid nanoparticles, as you can see, it has an IC value of about 60, and it does surpass that 50% viability. And then once we move on to that red line, which is the SQ-GEM nanoassemblies, we can see that their cell viability IC value decreases significantly. And so when we then encapsulate the nanoparticle with endelphysine, we can see that it further lowers the IC value, which shows that endelphysine encapsulation does provide further activity against those tumor cells with that lower IC value. Another important thing to note here is that the bone cancer cells used in this assay were actually pre-treated patient-derived cells. And so these cells have already been treated with other chemotherapy drugs. And so the fact that these nanoparticles do still have activity against these tumor cells indicate potential of these nanoparticles for their use in relapse patients or in patients where other chemotherapy treatments have failed. So several conclusions can be drawn from this research, and so the researchers were able to indicate using dynamic light scattering that a 1-to-1 ratio was the optimal concentrations for the nanoparticle in terms of size and PDI values. Additionally, various forms of TEM were able to indicate the supramolecular organization of the nanoparticles, and so they were able to indicate that these SQ-GEM nanoparticles, when they had no other drug encapsulated in them, they had this hexagonal organization. And then once endelphysine was encapsulated, they changed the supramolecular organization to more of an onion or spiral organization, which has optimal properties for a slow drug release. The researchers also used XPS in order to indicate the surface chemistry of the nanoparticle as well as the internal chemistry of the nanoparticle as well in terms of chemical composition. Finally, the researchers wanted to indicate the stability of the nanoparticles over time, and so they did this by analyzing the size as well as the PDI of the nanoparticles over a period of 60 days, and they indicate that when the nanoparticles are encapsulated with endelphysine, they are significantly more stable than when the SQ-GEMs are nanoparticles by themselves. The researchers also indicated the IC values of all of the nanoparticles studied, and they were able to indicate that endelphocene encapsulated nanoparticles do have increased activity against these tumor cells in vitro situations. And so the researchers in this article did have several future directions for their work as well that they specifically referenced. And so the future directions for this research were they wanted to use in vivo experiments in order to analyze the pharmacokinetics of the nanoparticles, as well as indicate the biodistribution of the nanoparticles and how the drug interacts with various types of tumors in vivo. Okay, and then there are my references. If you guys have any questions, I'll be happy to answer those on Wednesday, and thank you for listening.